textures, maybe an old concept, but it's now in 4.2, more on that a little bit later. Transform feedback instanced, enhancement to instance rendering that we have today, and it allows you to do even more with less CPU involvement. Another example coming. And then the shading language 420 pack is a set of smaller DLSL features that we folded into one extension. Okay, other stuff that I won't talk about outside of this slide, texture compression, BPTC, so the equivalent formats as the BC6 and BC7 formats in DirectX 11 and are part of core. Base instance, when doing instance rendering with, for example, GLDraw erase instance, you can now specify the offset into the buffer where the instance data is being pulled from. In an internal format query, it's a pretty simple API. You can find out the number of samples supported for different buffers, maybe floating point or integer buffers. Performance improvements. Compressed texture pixel storage. This allows you to modify an arbitrary subset of compressed data that you already have in host memory and download it directly. Blizzard actually requested this feature and we put it in 4.2. Shading language packing. I like this one too. You can put smaller data types like 16-bit or 8-bit data types and pack them tightly into a larger data type, UNT32. More on that a little bit later. Sampler initialization and uniform block binding initialization. You can now specify in the shading language your samplers locations or your UBO index locations. You don't need to call get uniform location and set the locations anymore in the API, so you prevent a stall in your software pipeline. Map buffer alignment. So we'd say that's almost an oversight when we did map buffer, but now it guarantees that the pointer that's returned is 64-byte aligned, so you can turn around, take that pointer, and use it in SSE or AVX instructions directly, and don't have to worry about alignments anymore. Conservative depth is a set functionality in the shading language that lets you give better hints to the graphics hardware and the driver on when it can actually do depth testing before it runs the fragment shader for you. Okay, immutable textures. So ARP texture storage provides a set of new API calls to create the format, shape, and container that holds textile data. So that shape, size, and format of the container itself is immutable, but of course you can still update the texture data in the container. As a bonus, your texture is always complete, so no more black data coming back from your texture when trying to do a texture lookup and you're scratching your head where that comes from. Image load store and atomic counters. I took this example from Cyril Crescent's blog, you might have seen it, where he did something really cool. He figured out to do single rendering paths for order independent transparency. So roughly how does it work? He has a fragment shader that writes to a layer in a 2D image array, and he uses image load store for that. Then the layer to write to, he actually tracks in another 2D image, and he updates that layer, that number with image atomic halves. And the result is an unordered list of fragments per pixel. So then there's one more pass needed to sort those with a simple full screen quad rendering, copy the fragment data in an array in GLSL, bubble stored in a composite data. He's shown that could be 1.5 to 2 times faster than other well-known algorithms that we're familiar with. Transform feedback instance example. So here's the need. I want to draw geometry multiple times, different rotations and locations on the screen. Maybe I created that geometry with tessellation added in CO 4.0. So for example, on this image here, that could be the doors and the arch from the swing of the doors. But I don't want to waste tessellation to retessellate every time. So what do? You tessellate the geometry only when your zoom level reality changes, and then you use transform feedback to capture the output of your tessellation. And with throughout transform feedback instance, you just feed that back through the pipeline n times, however many times you want, without any more CPU involvement and minimal load on the GPU. Pretty cool. Okay, compressed pixel texture storage. I have an example here. So here's the problem. We have application memory on the left, GPU memory on the right. You create a compressed texture, and that compressed texture has been downloaded onto the GPU memory. So now you want to update a subset here, the blue rectangle. And the question is, how do we do that most efficiently? Well, there's one easy way to download the whole thing. Not very fast, not very efficient, but it works. Second way, that's what you can probably, the most efficient way you can do it today. You take that updated region, store it in its own memory buffer that you allocated as the application, and then you call geocompressed text subimage2d to update it to the texture. And then lastly, with the new compressed pixel textual storage, we can just pull that directly out of your copy of the texture, your compressed copy of the texture, straight into GPU memory for you. Okay, shading language 420 pack, what's in there? Well, the first three are, I would call it convenience features, makes it a lot easier to program GLSLs. Not something you couldn't do today, but this definitely makes it easier. Binding layout qualifiers, that is talked about a little bit. And then on the bottom, more on the comment, you can stick any character in the comment if you want to. Shading language packing. This is the ability to pack multiple 8 and 16-bit values into a single 32-bit value for efficient shader processing, and maybe more importantly, reducing memory bandwidth. And if you're passing, say, data between shader stages, so for example, you pass something on a vertex to a fragment stage, you stick this in a variant variable, you could pack your 8 or 16-bit data into one UN32 variant, and it saves yourself some slots, memory bandwidth, and probably performance increasing because of that.